Hello everyone, welcome back to my DSA video series. This is my third video in the data structures and algorithm series. And in today's video, we are going to understand one of the most important graph algorithms, that is Dijkstra's algorithm. So don't worry if you have zero prior knowledge about graphs or algorithms. I'll be explaining everything step by step, starting from the basics using simple examples. By the end of this video, you'll clearly understand what Dijkstra's algorithm does, how it works step by step, and also why it does not allow negative weights. So let's get started. Before jumping into Dijkstra's algorithm, let's first understand a very basic question. What exactly is an algorithm? An algorithm is simply a step-by-step procedure to solve a problem. You can think of it like a recipe of cooking. Like you have the input, that means the ingredients, and there is a process, which means the cooking steps, and you get the output, the final dish. In the same way, in computer science, an algorithm takes some input, processes it through a series of steps, and then produces an output. Now that we understand what an algorithm is, let's move one step further and talk about paths. A path is simply a route that connects one point to another. Imagine cities connected by roads. Each city is a node and each road is a connection between nodes. A path is the sequence of nodes you travel through to go from one point to another. Among all possible paths, we usually want the best one. The shortest path is the path that has the minimum total cost. This cost could be distance, time, money. So even if there are multiple ways to reach the destination, the shortest path is the one that costs the least overall. Now you might wonder, why do we even care about these shortest paths? Shortest path problems are extremely important in real life. They help reduce travel time to save fuel and money, optimize resources. From GPS systems to logistics and delivery services, shortest paths help make decisions faster and smarter. So let's look at some real-world examples. Navigation apps like Google Maps use shortest path algorithms to find the fastest route. And network systems use them to send data efficiently. Even urban planning uses shortest paths to design better road networks. So this is not just theory, this is something used every day. So if shortest paths are so important, how do we find them efficiently? In a graph, there can be many possible paths between nodes. Manually checking all paths is slow, inefficient, and not practical. This is where Dijkstra's algorithm comes in. It automatically finds the shortest path efficiently, even in large graphs. Let's clearly understand what Dijkstra's algorithm is designed to do. Dijkstra's algorithm finds the shortest path from a single source node to all other nodes in a graph. It works for weighted graphs and positive edge weights. It uses a greedy approach, meaning it always chooses the best option available at that moment. To understand Dijkstra's algorithm, we must first understand graphs. A graph is a collection of nodes, also called vertices, and edges which connect nodes. Nodes represent locations or points, and edges represent connection between them. Graphs can be classified in different ways. In a directed graph, edges have a direction one way, and in an undirected graph, edges are two-way. A weighted graph assigns a value or cost to each edge, and this is the type of graph used in Dijkstra's algorithm. Now let's talk about something very important, edge weights. Edge weights represent distance, cost, and time. For example, a road between two cities might have a distance of 5 kilometers. In Dijkstra's algorithm, these weights must be positive values. Let's understand this with a simple example. If going A to B costs 5 and from B to C costs 3, then the total cost from A to C through B is 8. 5 plus 3 is equals to 8. If there's a direct path from A to C costing 10, the algorithm chooses the cheaper path, which is A to B and then B to C. Now let's understand how the algorithm actually works. We start from a source node. The distance to the source is set to 0 and all other nodes are set to infinity, meaning we don't know their distance yet. The algorithm repeatedly picks the nearest unvisited node, updates distances of its neighbors, and marks the node as visited. To do this efficiently, we use certain data structures. A priority queue helps us always select the node with the smallest distance. A distance array stores the shortest distance from the source to every node. A visited set ensures we don't process a node more than once. This process of updating distances is very important. Initially, only the source node has distance 0. All other nodes are set to infinity. As we explore the graph, we relax edges, meaning we check if a shorter path exists through the current node and update the distance if needed. Let's now look at a step-by-step example to make this very clear. This graph shows nodes connected with weighted edges. We'll apply Dijkstra's algorithm step by step to find the shortest paths. Step 1 is initialization. Set the source node distance to 0. Set all other nodes to infinity. This prepares the graph for distance updates. Next step, choose the unvisited node with the smallest distance. This node becomes the current node for exploration. Now we update distances. For each neighbor, calculate the new distance through the current node. If the new distance is smaller, update it. Once done, we finalize the node. Mark the node as visited so we don't process it again. This ensures correctness of the algorithm. Now let's find the shortest path from node A to node F using Dijkstra's algorithm. First, we start at node A, so the distance to A is 0, and all other nodes are set to infinity. From A, we look at its neighbors. A to B costs 2 and A to C costs 1. So we update the distances as B becomes 2 and C becomes 1. Now A is marked as visited. Among the unvisited nodes, C has the smallest distance, which is 1. So we move to node C. From C, going to D costs 1 plus 2, 3, and going to E costs 1 plus 5, 6. So we update, D becomes 3 and E becomes 6. Now C is marked as visited. Next, the smallest unvisited node is B with distance 2. From B, going to D costs 2 plus 3 equals 5. which is not better than 3. So no update. B is marked as visited. The next closest node is D with distance of 3. From D going to F costs 3 plus 3 equals 6. So we update, F becomes 6. We have now reached node F. The shortest path from A to F is A, C, D, F with a total cost of 6. Now let's look at a simple Java implementation of Dijkstra's algorithm. This code is written in a very basic way so that even beginners can understand it easily. Here, the graph is represented using a 2D array. If graph cost from I to j is not 0, it means there is an edge between the node I and node j, and the value represents the weight of that edge. A value of 0 means there is no direct connection. And after that, we have used two important arrays here. One is the distance array to store the shortest distance from the source node, and the visited array to track which nodes are already finalized. Initially, all distances are set to infinity except the source node, which is set to 0. To get, by using the getMinDistance function, we select the unvisited node with the smallest distance. This follows the greedy approach of Dijkstra's algorithm, always choosing the nearest node first. After selecting the nearest node, we check all its neighbors' nodes. If going through the current node gives a shorter path, we update the distance. This process is called relaxation, and it ensures that we always store the shortest known distance. Once a node is processed, we mark it as visited. So this ensures that we do not revisit the node because its shortest distance is already finalized. Finally, the algorithm prints the shortest distance from the source node to every other node in the graph. So this is a simple and clear implementation of Dijkstra's algorithm, showing how shortest paths are calculated step by step using a greedy approach. Now let's talk about an important limitation. Dijkstra's algorithm does not work with negative edge weights. Negative weights can mislead the algorithm into choosing incorrect paths. Let's understand why. Dijkstra uses a greedy approach, assuming the current shortest path is final. A negative edge can later reduce the total cost, breaking this assumption. That's why we use Bellman-Ford algorithm when negative weights are involved. Despite the limitation, Dijkstra's algorithm is extremely powerful. It is used in GPS navigation, network routing, robotics pathfinding. All these systems rely on fast and accurate shortest path calculations. Let's briefly talk about performance. Using a priority queue, we can find the time complexity and the space complexity. This makes it efficient even for large graphs. Let's summarize. We use Dijkstra's algorithm when all weights are positive and when we need shortest paths. Do not use it with negative weights. With that brings us to the end of today's video. We learned what Dijkstra's algorithm is, how it works, and where it's used. If you found this helpful, stay tuned for the next video in my DSA series. Thank you for watching.